Albert Einstein, a name synonymous with genius, began his life as a curious child in Ulm, Germany. From an early age, his inquisitive nature set him apart from his peers. Born in 1879, young Albert possessed an insatiable thirst for knowledge and a fascination with the workings of the natural world. His early years were marked by a relentless quest to understand the mysteries that surrounded him. A gift from his father, a simple compass, ignited a lifelong passion for unraveling the mysteries of the universe. This seemingly ordinary object became a catalyst for his boundless curiosity. The compass, with its unwavering needle always pointing north, sparked in him a profound sense of wonder about unseen forces. It was a tangible representation of the invisible laws that govern our world. This simple device became a symbol of the elegant and often hidden laws governing the cosmos. It was a reminder that even the most ordinary objects could hold the key to extraordinary discoveries. Einstein's curiosity was not confined to the realm of science. He was a polymath, with interests that spanned a wide array of disciplines. He developed a deep love for music, finding solace and inspiration in the melodies of Mozart and Beethoven. Music was not just a hobby for Einstein, it was a vital part of his intellectual and emotional life. Music for Einstein transcended language and provided a unique window into the human soul. It was a universal language that spoke to the deepest parts of his being. This appreciation for artistic beauty would later influence his approach to scientific inquiry, seeking elegance and simplicity in the laws that govern the universe. He believed that true understanding came from seeing the beauty in complexity. Despite his obvious intellectual gifts, Einstein's early education was not without its challenges. He often found himself at odds with the traditional methods of teaching. He often clashed with the rigid and rote learning methods of the traditional German school system. His teachers were frequently frustrated by his unconventional thinking and questioning nature. His independent mind craved a deeper understanding, seeking the why behind the what. He was not content with simply memorizing facts. He wanted to understand the underlying principles. This clash highlighted his innate desire to question, explore, and challenge conventional wisdom, traits that would define his scientific career. His relentless pursuit of knowledge would eventually lead him to groundbreaking discoveries. However, it was during his time in Switzerland, first at the Swiss Federal Polytechnic and later at the University of Zurich, that Einstein truly blossomed. These institutions provided the intellectual freedom he craved. Surrounded by an intellectually stimulating environment, he delved into the world of physics, mathematics, and philosophy, laying the groundwork for his revolutionary theories. His time in Switzerland was a period of intense growth and discovery. These formative years nurtured his unique approach to scientific inquiry, emphasizing intuition, thought experiments, and a deep connection to the fundamental principles governing the natural world. Einstein's journey was just beginning, and the world was about to witness the birth of a genius. Einstein's time in Zurich was pivotal in shaping his scientific thinking. The Swiss Federal Polytechnic, with its emphasis on experimental physics and practical applications, provided him with a strong foundation in the scientific method. He thrived in this environment, eagerly absorbing knowledge from renowned professors and engaging in lively debates with his peers. Equally influential were the informal discussions he had with his close circle of friends, known as the Olympia Academy. In these gatherings, fueled by coffee, pipe smoke, and a shared passion for knowledge, Einstein honed his ability to think critically and challenge established dogma. It was here that he began to question the absolute nature of space and time, concepts that were considered sacrosanct in classical physics. His readings of philosophers like Ernst Mach and David Hume further fueled his intellectual curiosity. Their critiques of absolute space and time resonated deeply with Einstein, prompting him to seek a more elegant and unified framework for understanding the universe. These philosophical influences highlighted the interconnectedness of seemingly disparate fields, encouraging Einstein to approach scientific problems from multiple perspectives. By the time he graduated from the University of Zurich in 1900, Einstein possessed a formidable intellect and a deep-seated desire to push the boundaries of scientific knowledge. He was ready to embark on a career that would forever change our understanding of the cosmos. The year 1905 is often referred to as Einstein's Annus Mirabilis, his miracle year, a period of extraordinary productivity and insight. It was during this period, while working as a patent clerk in Bern, Switzerland, that he published 4 groundbreaking papers that would revolutionize the world of physics, each addressing a different fundamental problem. One of these papers, on the photoelectric effect, earned him the Nobel Prize in Physics in 1921 and fundamentally altered our understanding of light, paving the way for future discoveries. The photoelectric effect, a phenomenon where light shining on a metal surface causes the emission of electrons, had puzzled physicists for years, defying explanation by classical theories. Classical physics, which described light as a wave, failed to explain why the effect depended on the frequency rather than the intensity of the light, leaving scientists searching for answers. Einstein's genius lay in his ability to connect the dots between seemingly unrelated phenomena, seeing patterns where others saw only confusion. Drawing upon Max Planck's work on quantized energy, Einstein proposed a radical idea. Light, in addition to its wave-like nature, could also behave as a stream of discrete packets of energy, which he called quanta, and are now known as photons, a concept that was revolutionary at the time. His theory elegantly explained the photoelectric effect. Only photons with sufficient energy determined by their frequency could dislodge electrons from the metal surface, providing a clear and concise explanation for the observed phenomena. This revolutionary concept that light exhibited both wave-like and particle-like properties laid the foundation for the development of quantum mechanics, a new and exciting field of physics, a field that would profoundly alter our understanding of the subatomic world, leading to numerous technological advancements and deeper insights into the nature of reality. Einstein's work on the photoelectric effect demonstrated his remarkable ability to challenge established paradigms and to envision entirely new ways of understanding the universe, showcasing his unparalleled creativity and intellect. While the photoelectric effect demonstrated Einstein's mastery of the quantum world, it was his special theory of relativity that truly cemented his place in the pantheon of scientific giants. This theory not only showcased his genius, but also fundamentally altered the way we perceive the universe. Published in 1905, this groundbreaking theory challenged the very foundations of Newtonian physics, revolutionizing our understanding of space, time, and motion. It was a bold departure from the classical mechanics that had dominated scientific thought for centuries. At the heart of special relativity lie 2 deceptively simple postulates. These postulates, though straightforward in their wording, have far-reaching consequences that continue to influence modern physics. First, the laws of physics are the same for all observers in uniform motion. This means that no matter how fast you are moving, the fundamental laws governing the universe remain consistent. Second, the speed of light in a vacuum is constant for all observers, regardless of their relative motion. This constancy of the speed of light is a cornerstone of special relativity and has profound implications for our understanding of the universe. These seemingly straightforward statements have profound implications, leading to a radical reimagining of our concepts of space and time. They force us to rethink the very fabric of reality and how we interact with it. One of the most startling consequences of special relativity is the relativity of simultaneity. The idea that 2 events that appear simultaneous to one observer may not be simultaneous to another observer in motion relative to the first. This concept challenges our everyday experiences and intuitions about time. This challenges our intuitive understanding of time as an absolute and unchanging entity. Instead, time becomes a more fluid and relative concept dependent on the observer's frame of reference. Furthermore, special relativity predicts that time slows down and length contracts for objects moving at speeds approaching the speed of light, a phenomenon known as time dilation and length contraction. These effects, though imperceptible at everyday speeds, become significant at velocities close to the speed of light. These effects, while negligible at everyday speeds, become increasingly significant as objects approach the speed of light. This has been confirmed through numerous experiments and observations, solidifying the theory's validity. Perhaps the most famous equation to emerge from special relativity is E equals mc squared, which expresses the equivalence of energy and mass. This equation has become one of the most recognized and celebrated formulas in all of science. This equation reveals that even a small amount of mass can be converted into an enormous amount of energy, a concept that would have profound implications for the development of nuclear energy. The realization of this principle has led to both the harnessing of nuclear power and the creation of nuclear weapons, forever changing the course of human history.